Scrutinize file entropy to isolate compressed binary streams from structured headers. High randomness indicates zlib or proprietary encryption, while low entropy reveals repeating mesh connectivity patterns. Identifying these zones allows you to target your reverse engineering efforts on the raw data rather than wasting time on encrypted noise. Locate known integer constants like node counts to determine byte order. If a 4-byte integer representing 1000 appears as 000003E8, the file uses big endian architecture. Recognizing this early prevents fundamental misinterpretation of every numeric value in the binary block. Scan for the characteristic hex sequences of single precision floating point numbers. Coordinates often cluster between 0 and 1, or large powers of 10, revealing 32-bit structures with predictable sign bits and exponents. This pattern recognition is the fastest way to find the bulk of the geometric data.
Identify the magic number at offset 0 to confirm the specific solver version. Proprietary headers often embed timestamps or software build IDs that dictate the internal memory alignment rules for all subsequent data blocks. This signature is your map to the specific structural layout used by that software release. Follow address references found in the file trailer. These pointers usually link back to the start of large result arrays, allowing the parser to skip irrelevant metadata and jump directly to nodal displacement vectors. Mastering these jumps is essential for navigating files that exceed several gigabytes in size. Note zero padded regions between record blocks. Computer-aided engineering solvers often align data structures to 8-byte boundaries to optimize CPU cache performance, creating predictable gaps that define the end of one record and the start of another. These zeros are not empty space, but markers of structural boundaries.
Identify repeating integer sequences to reverse engineer the connectivity list. A block of 4 integers per row likely defines first-order tetrahedral elements, where each value corresponds to a specific index in the global node table. Consistent increments in these values indicate sequential element numbering throughout the mesh. Switch your view to 64-bit doubles when analyzing high-fidelity simulation results. These 8-byte segments contain a 1-bit sign, an 11-bit exponent, and a 52-bit mantissa, providing the resolution required for structural deformation analysis. Misinterpreting these as two floats will result in complete garbage data. Search for ASCII strings within the binary mess to locate field variable names. Labels like stress or temperature often precede the actual numeric data, serving as anchors for manual offset calculation. These strings act as the only human-readable landmarks in an otherwise opaque proprietary format.
Compare two binary files with identical geometry but different load cases. The identical bytes represent the mesh structure, while the diverging bytes isolate the specific floating point values for nodal forces and boundary conditions. This differential analysis quickly narrows your search to the most relevant data segments. Examine individual bits within status bytes to decode visibility or material properties. A single byte might use bit masking to store 8 different Boolean flags, reducing the file footprint of massive models. You must look at the binary expansion of the hex value to see these toggles in action. Identify the compressed sparse row format by looking for 3 distinct arrays. One array stores the non-zero coefficients, another the column indices, and the third points to the start of each row. This efficiency is common in solvers to avoid storing the millions of zeros in a stiffness matrix.
Locate repeating structural blocks that indicate transient simulation steps. Each block usually starts with a floating point time value, followed by the full set of nodal results for that specific moment. Recognizing this repetition allows you to calculate the byte offset between each increment in the time domain. Identify string length by counting bytes until the first null character. In C++-based kernels, fixed-length character arrays are common, filling unused space with zeros until the predefined boundary is reached. This helps you define the exact record length for metadata fields like part names or material descriptions.
Verify the integrity of a block by calculating the cyclic redundancy check found at the end of the data stream. If your manual edits break the file, the solver will reject it because the stored hash no longer matches the content. You must update this hash to successfully inject modified data. Trace the file to its final bytes to find the global footer. Many proprietary formats store a table of contents here, providing the relative offsets needed to navigate the entire binary tree without a linear scan. This footer is often the most important part of the file for automated parsers.
Convert hex values to decimal using the Little Endian convention for Intel-based binary exports. Reordering the bytes from least significant to most significant allows you to read the physical coordinates of a mesh point directly. This step is mandatory before you can perform any meaningful data validation or extraction. Be alert for length prefixed records, where the first 4 bytes define the size of the following data packet. This dynamic structure allows the file to mix nodal coordinates, element definitions, and material properties in a single stream. Your parser must read this length value first to know when to stop.
Recognize displacement tensors by searching for groups of 3 floating point values. These represent the translation along the x, y, and z axes, usually ordered sequentially by node identification to minimize lookup overhead. In a hex editor, these appear as 3 similar-looking blocks of 4 or 8 bytes each. Determine if node IDs are stored as 16, 32, or 64-bit integers. Large-scale models with millions of elements require 64-bit addressing, which doubles the width of the integer columns. Misidentifying the bit depth will cause an immediate offset drift that ruins the entire parsing process.
Reverse the mapping from global to local indices by observing the element connectivity block. The integers here serve as pointers to the coordinate array, defining how points are wired together to form the physical mesh. Understanding this relationship is the key to reconstructing the geometry in external visualization tools. Detect applied constraints by looking for isolated integer blocks containing low values like 0, 1, or 2. These often act as enumeration types, signaling whether a node is fixed, pinned, or subjected to a force vector. These flags are usually found near the start of the simulation definition blocks. Identify material property assignments by finding a repeated integer value across a large set of elements. This index points to a smaller lookup table elsewhere in the file that contains the Young's modulus and Poisson's ratio. This indirect referencing keeps the element blocks small and efficient.
Calculate the header size by finding where the first repetitive data pattern begins. Subtracting the start address from the file origin gives you the exact byte count dedicated to metadata and solver-specific configuration strings. This constant offset is the foundation of your automated extraction script. Use hex patterns to locate specific element types within the mesh. Linear hex 8 elements will have 8 unique node indices, while quadratic elements will double this count, creating a distinct visual rhythm in the hex editor. Recognizing these rhythms allow you to visually scan for different component regions. Validate binary accuracy by comparing the hex representation to the expected text output. If the low-order bits differ, the solver might be using lower precision internal buffers, which can lead to cumulative errors in long-duration simulations. This check ensures your reverse-engineered data matches the solver's internal state. Distinguish structured grids from unstructured meshes by the presence of implicit connectivity. In structured grids, the neighbor relationships are calculated mathematically, so you will only find coordinate data and no explicit element connectivity lists. This drastically changes how you must approach the data reconstruction. Look for sub-step markers within the transient result blocks. These headers often contain the current iteration count and the residual error values, providing a window into the solver convergence behavior directly from the binary stream. Monitoring these residuals helps in debugging files from simulations that failed to converge. Verify tensor endianness by examining the symmetry of the stress matrix. If the off-diagonal components do not align as expected, you might be misinterpreting the byte order or the record padding within the tensor block. Symmetry is a physical requirement that serves as a perfect sanity check for your parser.
Extract the file version by searching for the first 4 bytes of the second header block. Newer versions of CAE software often introduce extra fields for advanced material models, which will shift the offsets of all subsequent results. Your code must detect this version to apply the correct offset map. Scan for small floating point values near the machine epsilon to find geometric tolerance settings. These constants define how the solver handles coincident nodes and small gaps between separate parts in a complex assembly. Identifying these helps in understanding why a mesh might be failing during the import phase. Identify load curve data by finding pairs of floats representing time and multiplier values. These tables are usually stored as continuous arrays, making them easy to extract and plot for validation against the input deck. Consistent spacing between these pairs often indicates a fixed time-step simulation.
Apply a binary search strategy to narrow down the location of a specific result. Change a single value in the hex editor, reload the file in the post-processor, and observe which nodal result is affected. This brute force method is often the only way to crack completely undocumented proprietary blocks. Detect the transition from binary data back to ASCII comments. Some formats wrap binary blocks in ASCII tags, similar to XML, requiring a parser that can handle mixed-mode streams without crashing on non-printable characters. These transitions often mark the start of new chapters in the simulation result file. Calculate the displacement magnitude from raw hex values to verify your coordinate system. If the computed values exceed realistic physical limits, you have likely misaligned your reading window by a few bytes. Real-world CAE results usually follow predictable scales relative to the original model dimensions.
Find the storage location of Jacobian determinants used in element quality checks. Solvers often pre-calculate these values and store them in the binary file to accelerate the calculation of the global stiffness matrix. These values are a goldmine for assessing the numerical health of a simulation mesh. Use memory mapping techniques to browse massive binary files without loading the entire content into RAM. This approach allows the hex editor to remain responsive while you jump between different gigabyte-sized result blocks. It is the only way to efficiently analyze results from large-scale, high-performance computing runs. Identify pointer swizzling, where memory addresses are converted to relative offsets before saving to disk. You must add the base address of the current block to these offsets to find the true location of the target data. This technique is used to ensure the binary file remains portable across different systems.
Analyze the header of a compressed block to find the original uncompressed size. This information is essential for allocating the correct buffer size before invoking decompression libraries, like zlib or LZO. Failure to provide enough space will result in memory corruption during the extraction process. Differentiate between nodal results and integration point results. Integration point data is often grouped by element and will contain more values per entity, corresponding to the specific quadrature rules used by the solver. You will see these as repeating patterns that are much denser than the standard nodal arrays. Search the header for unit system flags to ensure correct interpretation of the numeric data. A single integer code might signify that all lengths are in millimeters and all forces are in newtons. Without this context, your reverse-engineered values are just meaningless numbers without physical scale.
Locate the frequency and eigenvalue results by searching for a small array of floats at the start of a modal analysis block. Each value corresponds to a specific vibration mode shape stored subsequently in the file. These frequencies are usually the first thing an engineer looks for in a modal report. Identify contact interface definitions by looking for pairs of surface IDs. These blocks define which master and slave surfaces are checked for penetration, often using a sparse representation to save space. You can follow these IDs back to the element sets that form the interacting surfaces. Check the final byte of the file for a specific termination sequence. Missing or corrupted trailing bytes often cause the simulation software to report a premature end-of-file error, even if the primary data is intact. This check is your last line of defense against corrupted transfers or incomplete writes.
Automate the extraction process by writing a script that replicates the offset logic you discovered. This turns your manual hex editing insights into a robust tool for processing thousands of simulation files automatically. Moving from manual discovery to automated parsing is the ultimate goal of the reverse engineering workflow.